All right, today we're going to talk about the Compton effect. We're not going to spend a lot of time on the Compton effect. We're going to move on to matter waves, and in fact, we're not going to spend much time on those. But they are two profound things that will change the way you think about, well, almost everything. So the Compton effect is basically illustrated in this picture here, where you have this incoming X-ray photon right here. X-ray photon was shot at a target, and within the target there were some electrons, and the illustration kind of shows this idea that the X-ray photon came in, it was scattered, so it was deflected from traveling this way to traveling this way, and in the meantime the electron itself was also scattered. And at first glance, you might think, well, that's not very exciting. So a photon came in and bounced off an electron. What's the big deal? Well, the big deal is this. This is a photon. This is not a particle with any kind of mass or dimension or anything like that. This is totally different than the electron itself. This is not as if a billiard ball came in and struck another billiard ball. This is a piece of electromagnetic radiation interacting with a form of matter and scattering it, much like a two-dimensional collision. Now, the Compton scattering experiment, as it's called, comes with a lot of math, which is summarized in this illustration here, where the incident photon comes in, hits a target electron at rest. There's our target electron, or what now called the recoil electron, and here's the scattered photon. Now, this diagram shows something that Compton discovered, was that not only did the incident photon change direction, it also changed its wavelength. It came in as, in this case, violet light, and the outcoming one is more like along the lines of red. It shifted to something with a longer wavelength. Now, let's couple that with the fact that this electron at rest, mind you, meaning the momentum of this is 0 kilograms times meters per second. Now we have this electron taking off with some obviously greater than 0 momentum. Something's going on here more than we would expect when a piece of electromagnetic radiation, especially if we're thinking of this as a wave, this is considerably different than what you would expect would happen if a wave hit this. In fact, you kind of have to come to the conclusion that somehow this photon is behaving like a particle in its interaction with this electron. And indeed, that's what Compton showed through his experiment, this idea that the X-ray photon had momentum. So something that we traditionally think of, like let's go back to our previous studies, the momentum of any object was found using m times v, going way back to the beginning of this course. How do you talk about the momentum of something that doesn't even have a mass? And the speed is always the same. It's always 3 times 10 to the 8th meters per second. So this model, or this mathematical equation for momentum, is not going to work for our X-ray. So Compton came up with some new math and came up with this idea that the momentum of an X-ray, or better yet, the momentum of any part of the electromagnetic spectrum, any form of electromagnetic radiation, is equal to, well, look at this, shows up again, Planck's constant and divided by the wavelength. So going back to the experiment, remember this idea that when the incoming photon interacted with the electron gained momentum. Well, the X-ray must have lost momentum, and that's why you get this shifted wavelength. So while with particles, momentum is related to mass and velocity, and when velocity changes, momentum changes. Now we're looking at changes in wavelength or frequency to be attributed to the changes in momentum for an object that is part of the electromagnetic spectrum, the photon. Now you might think, talking pretty fast about something that seems important, what's really important is getting down to this end result here, the fact that now we can talk about photons as having momentum, A, and their momentum is given by this formula. It's worth noting, remember Planck's constant has two forms. And in the past, we kind of had to go with the flow. It could have been in electron volt form or in joule form, and we could kind of work with whichever one came our way. But in this case, if we are going to talk about classical units for momentum, then we need to use Planck's constant in its joule times second form. Not any debate around that. So you need to, when you want to get your momentum in units of kilograms times meters per second, you really need to use Planck's constant in this form. All right, so since we're on the roll of really radically changing our idea of light as a wave, we used to think light was a wave coming into this chapter, and then we saw things like the photoelectric effect kind of said maybe it's not a wave. Then we see this Compton effect, which suggests maybe it's not a wave as well. So we get rid of this wave idea and we say, no, light, let's not think of it as a wave or a particle. Light or electromagnetic radiation is a photon, and it has two kind of sides to it. Sometimes it behaves like a wave, and it sometimes behaves like a particle. And this is called wave-particle duality, this idea that something can behave under certain conditions, behaves like a wave, under other conditions, behave like a particle. When we do when we do refraction, when we do interference pattern, these kinds of things is where light or electromagnetic radiation shows its wave face. On the other hand, it shows its particle face when we do the photoelectric effect, we do the Compton experiment. So this is all well and good for something like a photon, because we really, I hope people came into this realizing that a photon is very unique, and it's not a shocker to find out that it's not exactly a wave, not exactly a particle. It's like nothing you would know. So we can change our view of this as we gather more evidence. On the other hand, let's talk about Louis de Broglie, because Louis de Broglie observed what was going on with the wave-particle duality of light and started to think really hard about any consequences this could have to other things. And mathematically, he realized that if this is the equation for the momentum of a form of matter, momentum is m times v, and this is the momentum of a photon, he wondered if you could equate these two equations and you rearranged it. He started to wonder. He developed a formula that said wavelength is equal to h over mv, which is just a neat mathematical trick, but it kind of suggested to de Broglie that you could get the wavelength of something that was a particle. So what de Broglie was basically saying was, you have wave-particle duality when it comes to photons, for sure. We saw this, we've seen examples, and there's tried and true experiments where we can show the wave behavior of light and the particle behavior of light. Now, de Broglie was suggesting that we might be able to look for wave-particle duality when it came to things that we traditionally think of as particles. So can we see wave-particle duality when it comes to particles? And the question really becomes, what would be the best convincer to you? What would we have to do to convince you that a particle behaves like a wave? I think if you wanted to prove to me that a particle behaves like a wave, you would have to do for me the one experiment that only works out or has definitive different end result for particles and waves. I would have to see an interference pattern equation. I'd have to see particles shot from a source in all directions go through a double slit, just like we can do with photons, just like we can do with waves. And I would like to see those things come through here. And if they behave like particles, they should go through these openings and end up on the other side. And then we should see 2 points where these particles hit. If it behaves like a wave, we would get a central maximum, we get another maximum, we get some other maximum along here. We would get an interference pattern for particles. If you could do that for me, if you could produce a double slit that we shot particles through, imagine we're spraying machine gun bullets towards these double slits. And all of a sudden the machine gun bullets don't just show up here or here, they show up here and they show up here and they show up here, as if somehow they've interfered with themselves constructively and destructively. Then I would be convinced of this wave-particle duality for a particle. Well, it turns out that you can do this experiment. You can shoot particles through a double slit and you can see an interference pattern. Unfortunately, it doesn't work for really large particles like elephants. If you shot elephants through a double slit, you would not see an interference pattern on the other side. It doesn't work for cannonballs. It doesn't work for bullets. It doesn't work until you get really small things, for example, electrons. But if you put electrons through a double slit, you can see an interference pattern displayed on the other side. You can put a screen, you can see evidence that electrons really do have situations where they can act like waves. So we've really entered this quantum world, the world of the very small, the world of the very weird, where particles don't just behave like particles, they sometimes act like waves.